Okay, welcome to week 7 of the semester. And we are still in chapter 4, which is a linear classification is the topic. And we'll wrap up that chapter today. We've covered it quite a bit. And there was one last section which I was debating whether to cover it or move on to the next topic, which is neural networks. That is chapter 5. But this last topic, I think, is interesting to those of you who are planning to do research in machine learning, and also it's a topic that keeps appearing in other areas. You might as well study it in one place before we say we're done with the linear classification. And this topic is variational logistic regression. All right. So we have studied logistic regression again and again. Project 1 was about logistic regression. And we said that's the main simple method for machine learning. And neural networks are just an expansion of those logistic regression methods. And last class, we covered something called Laplace approximation to an arbitrary distribution. So you see these machine learning methods somehow are learning the statistics of the data, right? It's purely statistics based, whether you like it or not. It's just looking at these examples and saying, this is what the data tells me. This is what the most likely answer for you is. So it's just statistical methods. And in order to make a prediction in logistic regression, using a Bayesian approach. The Bayesian approach is kind of interesting one in that it says, I will assume a prior distribution over the parameters. It's not like I don't know anything about the problem. I will assume a prior distribution. It tells me what the parameter value should be. There's some distribution. This value is most likely and this value is less likely and so on. And the data goes and modifies that. So prior distribution has nothing to do with the data. It's our prior assumption. So that's called PW. W is all the weights we need, and PW is the distribution over those weights. And we end up multiplying the prior distribution with the likelihood of the data. Likelihood is the probability of what you observe. Now you have some data which tells you what the classes are for this set of examples. And we associate a probability with that data set by multiplying the probabilities of each observed data point. We get a likelihood of the entire data set. And in the Bayesian approach, we multiply the likelihood with the prior to get the joint distribution of the data and the parameters, right? We get the joint, okay, of the output and the parameters. I should say of the output and the parameters. So the prediction is going to be marginalizing out the parameters, right? Because when we make a prediction, when the car is going to turn left or right, it doesn't care about what kind of parameters there are inside. So we say, let us marginalize out the parameters and then make the prediction. And we use the sum rule of probability, which involves integration. We'll take a look at that exact formula. So it involves that integration. And then in logistic regression, the Bayesian logistic regression, it involves a product of a sigmoidal likelihood function and a Gaussian. We usually assume a Gaussian over the prior distribution over the parameters. So it's a product of a sigmoid likelihood and a Gaussian, which is not a very tractable combination. And for this purpose, we want to replace the distribution with a closed Gaussian distribution. If it is Gaussian times Gaussian, we're integrating over, that becomes easy to make a prediction. So how do we get a Gaussian in place of some other distribution? And that is done first by using this Laplace approximation that gives you a Gaussian distribution. But it's not as good as a better approximation, which is called variational approximation. Variation tends to give you a better solution to the problem. So we bring in variational as a better way to approximate the distribution you're encountering for the data. And that's what we do here. Okay. All right, let's look at all the equations. And let me share the screen on this last set in chapter 4. Okay, this is called variational Bayesian logistic regression. Okay, so we have understood logistic regression, which is simply to find a set of weights with a set of inputs to be able to say yes or no, and it can be generalized to multi-classes. Bayesian says the weights have a prior distribution and not just to be learned only from the data. And variational says we're going to do some approximation, bring in some Gaussian distributions to play a role instead of the more complicated distributions that you will end up with. Because you'll need to integrate the product of the priors and the likelihoods and so on. So we're into this last topic in linear models for classification. We did discriminant functions, generative model, discriminative models, Laplace approximation, and we did Bayesian logistic regression. Today it's variational Bayesian logistic regression. So within variational Bayesian logistic regression, the subtopics here are Bayesian logistic regression posterior. So we're interested in the posterior distribution of the parameters. We start with the prior distribution of the parameters, and that becomes a posterior distribution of the parameters. So remember, in the Bayesian approach, we don't actually get a point estimate for the parameters. We don't say these are the values of W1, W2, W3, W4. We say that's going to have a distribution that with some values more likely than others. So which is where we have a distribution. To get any specific value, that's where we need to do the integration to get a specific value over the probability distribution. So the posterior distribution is different from the prior distribution. And then we bring in this phenomenal idea called KL divergence, Kullback-Leibler divergence. We see what is that? And that's a method. It's a very, very interesting method to approximate a probability distribution by another distribution. What's the best of those, right? And then how do we use all of that to do inference, which is to make a prediction? And a stochastic variational inference, some variation of variational inference called stochastic variational. So these are all mathematical topics, but I tell you, it's worth getting to know them. At least you know the terminology here, if not the method itself. So my goal is to try and teach you the method itself. And but you have to bear with me because we have to go through these steps about where does this integration come in and so on. So variational logistic regression, we say it's based on the calculus of variations. So that's a whole field of calculus itself, variational calculus. How a derivative of a functional changes, right? So we come up with a concept of a functional rather than function. All right, a function gobbles up a function and gives you a value. Right? It takes a whole function as input. Unlike a function, an ordinary function takes a value as input, produces a value as output. If functional takes a whole function as input, it produces a value as output. Anyway, we'll see that again. Approximation is more flexible than Laplace with additional variational parameters. So we are saying that the Laplacian approximation is a simple method, but this is a better method. So I think I showed this diagram. It's a nice diagram. And let's take a look at it again to motivate ourselves. So the data has a distribution in this yellow, right? This pale yellow color here. The input variable is taking values -2, -1, 0, 1, 2, 3, 4. And the yellow distribution says, hey, there's a peak over here at 0, and then it tails off here to 3. That's what the data looks like. And Laplace says, I'm going to find you a Gaussian whose mean is going to coincide with the mode of your distribution, saying, oh, look, this yellow distribution is a peak at this point, and this says, Laplace says, I'm going to give you a Gaussian with a peak right there, all right? So that's what Laplacian does. On the other hand, what we are exploring today is variational distribution. This is another Gaussian distribution shown in green here, which has more of an overlap with this yellow. It says, okay, I'm going to give you the best possible green distribution, Gaussian distribution, not just worrying about the mode, but about the entire area under the curve here. And this kind of is another diagram which shows for the red curve, the green curve, and the yellow curve, what the negative logarithms look like. And the red one looks like that, and the green one looks closer to the yellow one. Okay, so yellow one is like this. So green one is not perfect, but it is closer to the to the yellow one rather than the red one, which is out here. Maybe it doesn't show up as clearly, but look at this. Green is closer to this straight line than the red. Similarly, green is closer to the yellow line than the red. So green must be better, and green is the variational method. Okay, this is one slide where I try and summarize the entire Bayesian logistic regression, because we are going to go from there to define variational Bayesian logistic regression. So what we have are a data set D consisting of n samples. They're all pairs, x1, t1, xn, tn. X is the input vector, t is the, this should have been a scalar here, this is a scalar here. So t's are the target values, right? What is the value? There are n independent identically distributed samples. And we are assuming in this formulation that t is 0, 1. All right. Okay, t is 0, 1. So this is a two-class problem. And the parameters are W1 through Wm. There are m parameters. So the problem is a simple one. We multiply x by the w, right? And there are m parameters. And we assume that x is m-dimensional as well, all right? So we multiply each of these x's by the w's. And the probabilistic model specifies the joint distribution PDW. The joint distribution of the D consists of all the data, observed data, and the weights. So joint distribution, for any pair of variables, we can write the joint distribution as D given W times PW. So that is a uncontroversial statement to expand a joint by means of a conditional and a marginal by the product rule of probability, which is a product of a sigmoid likelihood and a Gaussian in the Bayesian case, the Bayesian logistic regression case. We are saying this W, the weights, they're going to have it's going to have a Gaussian distribution of this form given over here. So this says we are assuming that the weights have a normal distribution. W has a normal distribution with a certain mean and a certain covariance matrix, which we will assume to be very simple. So we say that is the Bayesian approach. Bayesian approach says I know something about the parameters. This is called the prior distribution. So we have that PW. PD given W is the likelihood function, that is the data given the weights. What is the probability assigned to the data by the set of weights you got? Well, it says that is defined by the binomial distribution. This is actually the Bernoulli. This is the Bernoulli distribution multiplied n times. You have n samples over here. So Bernoulli, it's only 0, 1 values. So what are these YNs here? The YN is P of C1 given Xn. So this is the probability of class 1 for the nth sample. That is nothing but sigmoid of W transpose Xn. So very cleverly constructed. So it says if you have an input X, the nth sample you got, the probability of it belonging to class 1, C1, let's say C1 and C1, C2, or however we define it as 0, 1 class, it's given by the sigmoid of the way. That's the probability that this model assigns. So the problem of maximum likelihood would be, well, what should be that W that's going to maximize this probability of all the samples you have observed? So that is the precise statement of the maximum likelihood estimation of the parameters. Okay. So in the Bayesian approach, goal is to approximate the posterior distribution PW given D. We were just using PW here. And we are saying, suppose when I give you the data, we want to approximate this posterior distribution, which is also a normalized product of the sigmoid likelihood and the Gaussian, right? So PW given D can be written as PD given W times PW divided by PD, right? So we essentially what to remember is PW is going to get replaced by PW given D. And we are saying, goal is to approximate the posterior distribution PW given D with a Gaussian, because PW given D involves a product of a sigmoid likelihood and a Gaussian here. This is a sigmoid likelihood and a Gaussian. The Gaussian QW. So we're saying that product can be replaced by a Gaussian, so we can use it in prediction. And what is prediction? Prediction is I give you a new X and tell me what's the probability of C1. Well, that is going to be given by sigmoid of W transpose X, right? Times QW. So this is the probability of D given W. That's what this part is, because we just saw that here. Sigma W transpose X here, right? And times Q of W is this part, which is we are going to be replacing PW given D by QW. DW means overall values of W. So this is the prediction problem, which involves a product of, in this case, it is overall the samples. That's this part here. And this is the distribution associated with the parameters. And by integrating out W, right, DW, right, we get the probability of this. So that is what's happening in this problem definition of Bayesian logistic regression. And we saw that this product here can be replaced by a Laplacian product. But we could make this one of these which is non-sigmoid into a Gaussian, or we can make it into or it's a Gaussian Laplacian, becomes a Gaussian. Okay, let's now try and understand what is meant by an important concept in machine learning called Kullback-Leibler divergence. So we'll attack that in a very simple way. Right, this is a fanciful example I came across in some statistics literature. It says a scientist is observing all these worms under his microscope or whatever, and he says that the worms have teeth. They all have teeth here. Observations of worm teeth. And then he counts how many teeth each worm has. And he makes a distribution here. So the worms have a distribution of 0 to 10 teeth. And this histogram is simply a count, right? How many did each have? 5 seems to be a very popular choice. Almost none had 0. Quite a few had 10. And he's plotting here a probability, which is not just a histogram. Histogram would have been just counts. He is dividing the count he's getting here by the total number of worms that he's got. So that gives you a probability, so that all these probabilities add up to 1, right? So that's what this is saying. We have x equal to x1 through x10 observations. P of x, what is the probability? That's what this plot is about. And all these probabilities together over 10 add up to 1. And let's say we are going to ask a question. What is this data? It looks like this. It's kind of going up here, coming down here, again going up. Maybe it looks like a COVID distribution, huh? Right? You have a peak and comes down and again goes up and whatnot. So we asked the question, I would like to approximate it by another distribution that is easy for me to work with rather than this complicated looking distribution. So the question being asked is, can we just replace it by a uniform distribution? That is, all these probabilities are equal, 0 through 10, which means we give each of them 1/10, probability of 0.1. Each of them, they'll all add up to 1, and that's one distribution. Another one is a clever distribution called a binomial distribution. Binomial looks somewhat Gaussian, if you might know binomial distribution. This is also going 0 to 10. It's got a peak around 5 or 6. This binomial, as this number becomes infinity, it's going to be Gaussian in shape. Okay, bell-shaped curve, right? But we only have 10 values, so it doesn't look quite Gaussian. And a binomial distribution has to be specified by 2 parameters called n and p. Right? Binomial has a relationship to the Bernoulli, the coin toss, right? In the coin toss, the 0-1 probabilities. Bernoulli is the number of heads when you make a certain number of tosses, right? So that's the probability p, right? So anyway, this is a Bernoulli. It's just a distribution. We're asking the question: is this approximated by this one uniform or by Bernoulli or binomial? Right? This is not Bernoulli. It's binomial. This binomial has to have some parameters. N equal to 10 in this case. And P is a certain probability, which is equivalent to the probability of heads, for example. That's what defines this. 10 equal to 10, let's say P equal to if we say the mean is 5.7, supposing we take the average of all of these and say, oh, what is the mean of this distribution, which is add all the values up and divide by the total. And that's going to give you the mean of the distribution. Well, let's just use that P equal to that mean. It implies that so we're using the mean over here, 5.7, implies that P is equal to 0.57. Anyway, this is it requires a parameter called P. This approximation has more subtlety, but is not perfect. This is kind of a very rough distribution. Everything is equal. This is saying, no, what about we assume a Gaussian shape like this and say, okay, is this better than this is the question? Because this I can work with. It's got a simple mathematical form. This has a simple mathematical form. This one does not have a simple mathematical form. So the question is, which one is better? So Kullback-Leibler divergence says, I'll tell you what is a measure of the goodness of these two. That's the KL divergence between P and Q. We can also compute the KL divergence between P and this Q. So which one is smaller? KL divergence is like a distance. It's not quite a metric, but that's a measure of how close they are. So this slide here explains what the KL divergence between distributions is. KL divergence has got something to do with entropy. Supposing I give you a distribution P, which is like the Pxi we had, and I ask you, what is the entropy of that distribution? So the entropy of that distribution is HP equal to summation I equal to 1 through n pxi log pxi. So I can calculate for this distribution out here, what is its entropy? That is when I look at a worm and it has a number associated with the teeth, how much information am I getting? We say that if all of them are equally likely, you're going to get a pretty low information because they're all the same. So you get no information. But if I get observe one, maybe I get more information here, and this one also maybe more information here. So entropy entropy is a functional. It takes a full distribution as input. P is a full distribution, different values for different inputs. It's computed like this: pxi log pxi. If you take this log to the base 2, it's the minimum number of bits needed to encode the information. So it relates to this fact: how much information are you getting when you know a value from the distribution? In the trivial case, supposing you had only 2 values of the teeth, not 10 values, and both of them are px1 equal to px2 equal to 1/2, and I give a reading for one of them, how much information did you get? Okay, so it says 1 bit is needed for that. Okay? Pi log pi. So you get 1 bit of information if both are equally likely. So anyway, that's an interpretation of what does entropy measure, is how much information do you get? If the distribution is uniform, then you get more information. If the distribution is non-uniform, you get less information because you have more chance of what it could be. If it's 0.8 and 0.2, you get less information. KL divergence is a slight modification of entropy. It says decay. So how do you define the entropy between 2 distributions? It says it's summation pxi log pxi minus log qxi. So this says, supposing I replace my p distribution with a q distribution, the KL divergence between the two is written like this. And we say that is the expected value of log px minus log qx. Taking a logarithm of the probabilities, expected value over all the samples you have got. Now it has got an information theoretic interpretation. It's the number of bits we expect to lose in encoding P by Q. So if you're going to replace your P by Q, you're losing information. And this measures how much information you're going to lose by one or the other. So now we have a way of measuring the teeth distribution of the worms, first by a uniform distribution and then by a binomial distribution. Which one is better? Well, if you do that calculation, the Kullback-Leibler divergence between the observed data and the uniform data was 0.338. Kullback-Leibler divergence between the observed data and that binomial distribution was 0.477. So this is information lost from binomial approximation is more than with uniform. So binomial is losing more. Okay, that was unexpected. It looked a little like it had some information in it, but KL divergence says your uniform is better. All of them same. Okay, so be it. That's a kind of measure. KL divergence is not a distance measure since it is not symmetric. So if you do binomial to observed or observed to binomial, if you did binomial to observed, you get 0.33. Oh, that's much better. Maybe this will also change. So that's something to know about KL divergence. So constantly in machine learning, we are talking about optimizing using KL divergence. We're talking about models of probability distributions. And this says, we insist on modeling the data by a binomial distribution, although we just saw that the uniform was the better one. This says which binomial is the best. So they're plotting value of P. Let's change the value of P. There's only parameter at our disposal. And we compute the KL divergence with our data set. And it says the KL divergence keeps going down from 0.3 something. It's going down here. It goes down to almost 0 here. Oh, wow, that's good. So there is a binomial distribution that's going to make this KL divergence small, and it again goes up like that. So this is the optimal value of P. So this says, supposing I insist on modeling our data by a binomial distribution, if we minimize the KL divergence, we can find the value that we're looking for. Supposing we are headstrong and we say, hey, I don't want to use a binomial. I want to use this peculiar distribution here that is defined by a family like this. We call the binomial family because all you need to do is change the P and you get a different binomial, right? So you can call all of it as binomial family. This one is a strange distribution that is giving all of these values the same here. And then after teeth count goes from 5 to 6, all of these have the same value, right? So we say in the interval 0 to 5, the probability is given by 1 minus p, some value p, 1 minus p or 6. And the value from 6 to 10 is equal to p or 5. If you add up all these numbers, it should add up to 1, of course, right? So this is how we define. It's a very peculiar distribution. Half the time it's one value, other half the time it's another value. Right? So if we say this is the family, only thing at our disposal is this value of P. The P can be small or large. That will allow you to change this. And among all those distributions, what value of P will give it the best? And we compute KL divergence with our data set. Say, oh, look at this. P equal to 0.47. KL divergence is 0.338, right? I guess this is a scaled value. This looks like 3 over here. Okay. Oh, I see. Yeah, it's okay. It's 1, 2, 3. So 0.338 is somewhere over here. Yeah. So this says that's the best KL divergence. So the minimum KL divergence occurs at 0.47. Since this distribution is close to the uniform distribution, we don't save anything. This is close to uniform distribution. So you get 0.338, which was not much better than the other one we saw, 0.33 something for uniform. Key point is that KL divergence can be used as an objective function to find the optimal value for any approximating distribution. While this example is optimizing a single parameter, we can extend it to a model with many parameters. There's only one parameter, P here, that is defining this family. Binomial also had only one parameter, P. So in general, you're going to have many parameters. So this is saying that your worldly data may have a certain complicated distribution, but I'm going to say, I'm going to replace it by something which is kind of much simpler to work with, particularly if you have to do integrations and so on to making predictions. So anyway, this slide is a do-nothing slide. It says function versus functional. Function takes a value of a variable as input and returns the function value as output. Functional takes a function as input and it's a functional value as output. So this is a functional. H of p of x is a value. This 0.338 is the value for this distribution. That's a functional. Entropy is a functional. And we work with the calculus of variations. Function input x is a value, returns a value y, whereas the functional input is a function yx, returns a value f of yx. Standard calculus concerns derivatives of functions, how output changes in response to small changes in input. That's what standard calculus does. How does output change with respect to small changes in input? Variational calculus concerns functional derivatives. So you have their own derivative. How output changes in response to infinitesimal changes in the input function. If I change the distribution a little bit, how much does the output change? Output is a functional. So we studied that part of it. And so we also have things like functional derivative derived by considering how the value of functional f of I changes when the function y of x is changed to y of x plus epsilon eta of x. So for example, we have y of x is this red function. It's a function y of input x. We are changing the function y itself. It's y of x plus epsilon eta of x, a small change. And that function could become this blue function. Right? Just like we have functions, your functionals can also change. And maximizing a functional or minimizing a functional. And this Kullback-Leibler divergence we just talked about leads to a functional that we need to minimize. Okay, common problem in conventional calculus, find values of x that maximizes a function y of x. Calculus of variations, find a function y of x that maximizes a function. So which function is best? Example, find a function that maximizes entropy. Right. And what is the use of functional calculus or variational calculus? Well, it's useful in machine learning, but interestingly, here is something very interesting, that it is this variational calculus is what is needed to show that the shortest path between 2 points is a straight line. Isn't that interesting? How would you prove that the shortest path between 2 points is a straight line? It sounds like a very fundamental question in mathematics or geometry, right? It says to show that you need the calculus of variations. You can also use this calculus of variations to show that a distribution that maximizes entropy. It says if you have a distribution over x and over all possible distributions of p of x, which one will maximize the entropy of that distribution, which we just defined? That is integral of px log x over all x. Turns out the Gaussian is what that distribution is going to be. Maximum information content is given by the Gaussian. So why is this so interesting? Is we often talk about how data in nature is going to be Gaussian, right? There's going to be a peak and then there is a tail, on either side. And that's a Gaussian distribution. And this says that is the distribution that maximizes the information. If there's a lot of variability in your input, it's going to be Gaussian. And this shows you that's the reason, okay? So anyway, so a couple of profound philosophical statements in the middle of this lecture. Okay, variational methods there's nothing intrinsically approximate about them, but they naturally lend themselves to approximation by restricting the range of functions. Example, quadratic. We can say we are going to restrict ourselves. We just saw that binomial was a restriction. Quadratic linear combination of fixed basis functions. So on, some assumptions will, but the variational method is general. And we apply it to probabilistic inference, a fully Bayesian model. All parameters are given prior distributions. A fully Bayesian machine learning model will have a whole bunch of parameters, but we say they all have prior distributions. Model may have latent variables as well as parameters. So you can define Bayesian methods for a neural network or even a deep network, which has not only got observable units, but also hidden units whose values you don't know. And we can have a Bayesian distribution over all these. And denote all parameters and latent variables by Z. Denote set of observed variables by X. Given n independent identically distributed samples for which X and Z, the probabilistic model specifies posterior distribution P of Z given X, as well as model evidence P of X, right? So this is probabilistic inference. Within a model, you can have a distribution over the hidden variables, okay, for a given set of observations where we are. So in probabilistic inference, we can do that, as well as associate some evidence, the probability to the evidence, the input X. Okay, now we are back to Bayesian logistic regression. I kind of took a side trip right now, if you noticed. I ended up telling you about entropy and Kullback-Leibler divergence and all that kind of stuff, you know. And there was a little bit of a side trip. The reason I took the side trip was the next step in variational Bayesian logistic regression involves invoking the Kullback-Leibler divergence. Because remember, after all, we are trying to approximate one distribution by another distribution. So this says, here is an equation that looks kind of scary in the beginning, but it turns out to be an identity that one can prove that if I have D, this is just an algebraic equation, but we specifically put in this as a probability of the data. Log probability of the data can be written as a log. This is not log, this is actually a function L, I believe we call it as a loss, right? Lower, but not loss, it's a lower bound. L for lower, but see, L is used for all kinds of things in machine learning. N can be loss. In this case, it's a lower bound, LQ plus KL of Q and P. We just understood what KL stands for. It's a measure, it's a number. It's a number that measures how similar Q and P are. All right. And what is this? PD is written in terms of PQ and P. Well, there's a relationship. LQ is defined as integral Q of W. We're bringing in these W, the weights here, logarithm of PdW over QW times DW. All right, so this is a product here. It's some kind of a ratio over here. It brings in a P and a Q, the logarithm of that QW. We're kind of integrating something out. And this thing is a functional, we say, because it takes Q as input. What is Q? Q is going to be our approximating distribution we're going to be using in our modeling. So it says that functional can be written as an integral. An integral always gives you a value, okay, a number. And so that is this first term. So we are tying in D with Q and P over here. And KL of QP is the standard definition of Kullback-Leibler divergence. This equation is integral of QW logarithm of PW given D and over QW DW. So this D comes in only because we are going to be using the posterior for the W here. Okay, it's just like we had PW, PW given D. So this is the equation that is important. So you have to familiarize yourself with this lower bound and then the Kullback-Leibler divergence between Q and P, where W is given the data. All right, so that's Kullback-Leibler. So what is this? We wish to maximize ln of PD, it's this quantity called evidence, by a suitable choice of Q. This is saying you have to choose some Q that's going to maximize the probability of the data. And that requires, we want to minimize KL divergence over a family for QW. It says, if you want to maximize this quantity, you want to make this KL divergence to be as small as possible, right? We want KL. KL divergence is a negative quantity here. Okay, that's why. It's a negative quantity. That's what's going in here. We want to make that because it's going to make this small. So we want to increase this. So it says, okay, then make KL as small as possible, ideally 0. So which finds distribution QW that best approximates PW given D. So this says we want to minimize this KL divergence, which finds the distribution QW that approximates PW given T. So this says if you do this optimization properly, you're going to find a Q of W that's going to be best modeling. If these two are equal, this whole thing becomes zero. QW is the same as PW given D, then it's going to be zero. So I know this is not easy when you first look at it, but let me assure you that this is a useful thing, not only for Bayesian logistic regression, but also a whole host of methods. You will encounter variational autoencoders as one topic, and other methods of approximate inference you come across in machine learning. All of them keep on referring to the idea of Kullback-Leibler divergence to find the distribution that models your data as well as possible. Okay, so lower bound on PD is LQ. Maximizing the lower bound LQ with respect to distribution QW is equivalent to minimizing KL divergence. When KL divergence vanishes, Q of W equal to Q of W is equal to P of W given D. Plan. We seek a distribution QW for which LQ is largest. So this says you want a distribution for which LQ is largest. And we consider a restricted family for QW. LQ is just a measure, lower bound. So I give you a Q and just it calculates L of Q, which involves the data and this Q, the form of Q and the P, the data also. We consider a restricted family for QW and seek member of this family for which this KL divergence is minimized. Member of this family means something, some version of binomial, some version of the other one we saw. So variational inference, we want to form our Gaussian approximation Q of mu sigma by n of mu of n of W given mu sigma. So we are restricting ourselves saying that Q is going to be Gaussians, right? That's what we wanted. So we're going to be using Q to the posterior P by minimizing the KL divergence. All right, so this is the KL divergence is being written here, DKL between these two, or expected value over the samples of the ratio we had. So this is the KL divergence between the Q and the P is the expected value of this quantity over all the sample over the data set. Expectation with respect to a data set, that's what it is. And we fit the variational parameters mu and sigma, not the original parameters W. Although there's an interpretation that mu is an estimate of W, while sigma indicates a credible range where parameters could be plausibly around this estimate. So it says find that mu and sigma such that best fits, that is the best possible Q for fitting your data, PD. Criterion to minimize is this quantity. As we can only evaluate the posterior up to a constant, we write DKL like this, okay? And we say we want to minimize this quantity because DKL greater than equal. The Kullback-Leibler divergence is always positive. That's something to remember. When you take a measure between two distributions, you're going to get a positive value. You're not going to get a negative value. DKL is greater than or equal to 0. We obtain a lower bound on the model likelihood. And that lower bound is that is log P of D is greater than or equal to minus J. And what is the J is this quantity, all right? So this quantity is going to be a lower bound on log P of D, and this minus J is called the evidence lower bound or elbow, all right? That's another term useful in machine learning. We refer to elbow. Evidence lower bound is the negative of this quantity here, all right? And that is going to be negative of this, okay? So we want DKL to be made as small as possible, and it's going to be the negative of this quantity. And and we say that it's going to be larger. The log P of D is going to be larger than this. So you got to look at all the inequalities here, which is positive, which is negative, to conclude that log P of D is greater than or equal to minus J. For logistic regression model and prior, this J is, we plugged in here the form of the logistic regression. Sigmoid of W transpose Xn comes in, and we say that this is a quantity we minimize. Why do we want to minimize this? Because at negative J, we want to maximize log PD. And to maximize log PD, we want to minimize this quantity J. All right. So that is basically the criterion J. We could evaluate this expression numerically. The first two expectations can be computed analytically. The remaining n terms in the sum can be reduced to a one-dimensional integral. We could similarly evaluate the derivatives with mu and sigma and fit the variational parameters with a gradient-based optimizer. However, the inner loop for each function evaluation would require n numerical integrations or further approximations. So there is a variation of this called stochastic variational inference. We can avoid a numerical integration by simple Monte Carlo estimate of the expectation. So this is a Monte Carlo summation. We get a number of samples and divide by the total number. And the real cheap estimate to use one sample to come up with an estimate of J. So removing dependence on J and mu. So remember that we are after a mu and a sigma for the Gaussian distribution. Don't forget that what we are after. We're trying to replace a distribution by a Gaussian. That's what the Laplace method was. So this is also doing the same thing. And the goal is to move the variational parameter mu and sigma, which express which weights are plausible so that the cost J gets smaller on average. We can remove the variational parameters from the random draws by writing down how a Gaussian random number generator works. And yeah, this kind of stuff actually shows up in variational autoencoders. Okay. Minimizing cost function J, we can minimize the cost function J by stochastic gradient descent. We draw a data point and at random, some Gaussian white noise V, and evaluate J and its derivatives. We then make a small change to mu and sigma and repeat. All right, that's what it takes to do variational Bayesian logistic regression. All right. So, I encourage you to explore these ideas and say, let me try it out. It looks complicated, but I'm going to try and see if I can put it all together. Okay, this is applicable to neural networks. While some of the fine details are slightly complicated, none of them depend on the fact we were considering only logistic regression. We could usually replace the logistic function with another model likelihood, such as from a neural network, another model likelihood. As long as we can differentiate the log likelihood, we can apply stochastic variational inference. All right, what does all this do for you? The two, we're in chapter 4, which is about linear classifiers. I give you some red circles and red crosses and ask you separate the two. Find me the mathematical function that separates the two. And predictive distributions. And PC1 given phi is plotted. All right. And so PC1 given phi, well, that is class C1. So that particular probability is 0.66, 0.75, 0.25, like that. So you're getting a different boundaries, all right, for different values of the probability. You want, of course, the maximum value, which is probably 0.75 is the best one. So that's where you draw your boundary. So this is a predictive distribution. You see, this Bayesian method is all probabilistic. And that's how you're going to be separating the classes. This is what the variational Bayesian logistic regression solution to the problem is. And if you're saying, look, just give me the decision boundaries between the classes, and again, we have corresponding to each of these values. The maximum is what you would want to choose, 0.66, 0.75. And these are the decision boundaries between the linear decision boundaries between the classes, and these are the distribution. The distributions are not the boundaries themselves. And this is the linear decision boundary drawn by the logistic regression, which is a sigmoid cut function in the linear boundary, W transpose X, right? That's what it is. So what is the values of W? So large margin solution of SVM has qualitatively similar result to the Bayesian solution. Okay. All right, I went over a complicated topic in the hope that you were fascinated by what it takes to come up with a Bayesian solution. There's no simple way to express the complicated things that are going on here. We have prior distribution for the parameters, and we end up with a posterior distribution parameter. Use the posterior distribution in some integration to do the prediction. So there's no way of getting around all of this. You have to use all of it. And by using the variational method, you can get a Gaussian approximation, just like you can do with Laplacian, except you get a better solution using this approach, right? So what if you redid your project one, which you did with simple logistic regression? You used the frequentist approach, right, which is maximum likelihood solution to the problem. Now you say, oh, I'm going to try a Bayesian solution. Your performance may not improve all that much, because that all it required was, I mean, you had plenty of data also, right? If you don't have enough data, the Bayesian is a good way to go. Okay. All right, I'll leave you with that story. And Mihir, is it a good time for you to take over?
Yes, Professor, we can start with the quiz now.
Okay. All right. Mihir tells me the quiz is about what we did last week, right? Where we covered among other things, Laplace approximation was one of them, right? What else did we cover?
IRLS solution for linear and
Second
logistic.
order. You know, I mentioned that I mentioned so many names of mathematicians in this course. You know, we've talked about Taylor series. We mentioned Lagrangian optimization, and we talked about Newton-Raphson, which is the IRLS method, and we talked about Hessian matrix of second derivatives, and then we talk about Jacob, I guess his name, Jacobian vector, so on. So many male mathematicians, right? One day we'll cover some, women mathematicians also, and give them some names, I hope. Okay. All right, then I'm going to stop sharing, and then we're going to stop the recording.